Yes, sir, please.
Yeah. So coming to the convention for scalar and multi-bonds, uh, suppose you have a transformer element connected like this. You have two bonds. So here the power is coming into this transformer element and it is leaving this transformer element. Power is a product of effort 1 and flow 1, and effort 2 and flow 2 it's leaving. Now transformer is a device which is not going to keep power with itself. Whatever comes in will leave. Now the relationship between the variables of power is such that flow 2 is equal to mu times flow 1, and because it's a power conserving transformer, uh, E1 F1 will be equal to E2 F2. You can therefore write F2 as mu F1 here, and then when you compare the left hand side and the right hand side and arrange it, you can see that E1 is equal to mu times E2. So while you specified that F2 is equal to mu times F1, because of the power conserving nature of the transformer, automatically you got the relationship E1 is equal to mu E2. In multi-bonds, something similar takes place, except there is a subtle difference. Suppose you have a multi-bond of cardinality n with vectors E1 and F1, and you have the other bond connected to the transformer with cardinality m, and you have E2 and F2 as the vectors. Now, power coming in and power leaving out is the same. So let's say that you have the matrix A, which is actually uh, playing the same role as mu here, except that it's a matrix here because it's a multi-bond. So F2 is equal to A operating on F1. This is the flow relationship. And because it's a power conserving, it could be A could be a M by N matrix in this case. Now, because it's a power conserving transformer, the power balance has to be there. So if you substitute F2 is equal to A F1, you get, and rearranging it, you will automatically get E1 is equal to A transpose E2. So while you started with F2 is equal to A F1, automatically you got E1 is equal to A transpose E2. Now, this is the care which you have to take when you're dealing with multi-bonds. In the software which you use for bond graph, all these things are usually taken care of. But when you are applying bond graph, when you're doing modeling, it's essential to know this subtle difference. Now, for modeling a rigid body, so you have this rigid body, it has a center of mass, it has a particular orientation with respect to the inertial frame. And let's say that uh, you know the motion of the center of mass, you know the angular velocity with which this body is moving, and you know the location of each and every point on this body with respect to the center of mass. So you have a velocity relationship like this. If it's a rigid body, you have the velocity relationship for the ith particle. The velocity of the ith particle is equal to the velocity of the center of mass minus r cross omega. So this is a kinematic relationship, and we represent it in bond graph using these two junctions. So this one junction here represents the velocity of the center of mass. It's the translational velocity of the center of mass. We also have this one junction here, which is representing the angular velocity of this body with respect to the inertial frame. So there is a frame which is frame B, which is fixed on this body. So as the body moves, as the body changes its orientation with the angular velocity omega b with respect to 0 in the frame 0, so its orientation with respect to the frame 0 changes, and the rate at which that takes place is omega. So you have these two junctions. So it's very simple to start with bond graph. You have this kinematic relationship. We will just say that if I want the velocity of the point 1, it can be written as the velocity of the center of mass minus r dot 1 with respect to c in the frame 0. So this becomes uh, r1 with respect to c in the frame 0 cross operating on omega. So this kinematic relationship is taken care of for the point 1. In the same way, you can do it for all the other points. Let's say you have the point n. So the velocity of the point n is equal to the velocity of the center of mass minus r cross omega. You can assign the inertia on this kinematic structure. So this is what you've got is just a pure kinematic structure. There was no dynamics in this. Now you bring in the dynamics. So you bring in the inertias. So for translational inertia, you have the inertia due to the mass of the body, as if all of it is located at the center. And you can, it has an angular momentum, it has a linear momentum. The momentum of the mass of the body B expressed in the frame 0. And this rate of change of this momentum, okay, is taken by this I element, and it is caused by the summation of all these forces F1, F2 up to Fn. So the rate of change of linear momentum of the body P is caused by the resultant of the forces acting on this rigid body. Now we come to the rotational part. So here you have the one junction representing the angular velocity. So here you have the I element representing the inertia tensor of the body. It's a matrix, it's a square matrix. It's the inertia tensor of the body about its center of mass and expressed in the inertial frame 0. So when you deal with this inertia, you're actually contributing a state which is the angular momentum of the body about the center of mass expressed in the frame 0. The rate at which this angular momentum changes is caused by the resultant of these moments. Moments due to these forces which were acting at these points, they create moments about the center of mass. And the resultant of all these moments results in the change in the angular momentum of this body about its center of mass. So you can also have additional moments in the form of torques, and they will all add up. So you have the rate of change of the angular momentum of the body about the center of mass expressed in the frame 0, inertial frame 0, is equal to the resultant of the moments of these forces about the center of mass plus the resultant of all the external torques that are acting on this body. So you can see that in this module that you have got here, you have captured both the translational dynamics as well as the rotational dynamics. So this is for a single rigid body. And you can see that this model, you started with kinematics and then you appended the inertia, and then you are able to obtain the dynamics of this rigid body. So this is the beauty. You can directly start with the kinematics and then you can append dynamics to it. There's one more essential kinematic relationship which is involved, and that is regarding orientation, how to obtain the orientation. So here you have the rate of change of the orientation matrix is equal to omega cross the orientation matrix. And the columns of the orientation matrix are the unit vectors. So the rate at which the I vector changes is equal to omega cross I, because they are fixed magnitude vectors. They only change their directions with an angular velocity of omega. So when you compile this, you can obtain from the one junction representing the angular velocity of the body, you can obtain this information. That is, you can obtain all the columns of the orientation matrix. So I, J, and K. So when you compile them together, you get all the three columns of the orientation matrix. That is how you can obtain the orientation matrix. It's actually represented by a single differential equation, matrix differential equation like this. The expression of dynamics in the rotation, in the moving frame, it's not as simple as it was what you saw in the inertial frame. There both the rotational as well as the translational dynamics appear to have a Newtonian kind of form. Here you have a slight difference. Now, I'm not going into the mathematics of this right now due to shortage of time, but you can see that the rate of change of the angular momentum of the body about its center of mass, when it is expressed in the frame B, which is moving, the body frame which is moving, it is equal to minus omega cross P, omega cross the angular momentum, plus the resultant of the moments expressed in the moving frame, plus the resultant of the external torques expressed in the moving frame. You see, all these quantities are expressed in the moving frame. But you have an additional term here, which is the gyrostor term. So this is the one which is producing our gyroscopic effect. And this is happening because we are dealing with the dynamics, rotational dynamics in the moving frame. When you represent it in the moving frame, this is the component which is the gyrator or gyrostor component. Expressing translation in the moving frame also, when you do that, you can also have the rate at which this particular quantity, but it results in the expression of velocity, which is the expression of velocity of the center of mass of the body observed in the frame 0, expressed in the frame 0, but then thereafter expressed in the frame B. When you take the derivative of this, the rate at which this momentum quantity changes is actually equal to the resultant of the forces, but also an additional term comes into picture, which is omega cross this. And this is also somewhat like your, it's a gyrostor term, additional gyrostor term. Now this gyrostor term is actually what we call as the Euler junction structure here. So when you express the dynamics in the moving frame, so you have the translational dynamics in the moving frame, you have the rotational dynamics in the moving frame. Unlike the inertial frame, you have an additional dynamics here, which is the Euler junction structure. And this comes just because you are expressing the rotation in the moving frame. So this is the dynamics formulated, rotational dynamics formulated in the moving frame. Sir Isaac Newton, we credit him with the translational dynamics, and Leonhard Euler, in fact, we credit him with the rotational dynamics, but not only the rotational dynamics, but also with translational dynamics, because the way in which he represented these equations of dynamics in the mathematical form that we know of today, they are due to Leonhard Euler. Even the Newton's laws, they were not written in the form that we know of today. rate of change of momentum is caused by the resultant of external forces acting on the body. So it was Euler who formulated these laws in the form of the mathematics that we know of today. Uh, so this is as far as the rigid body mechanics is concerned. We now go to some prosthetic mechanisms and the string tube actuation system. We applied this idea of robotics and mechanics to prosthetic systems, which is also a very useful application of robotic systems. Uh, if you see your hand, you have the fingers which can curl in and out. So your fingers can go in and out in what we call as it's a closing of the fingers, and when you're opening up the fingers. So when you're closing the fingers, uh, you can realize this using a mechanism like this. You have a finger, you have a joint like this. There's a pulley which is mounted on this. It can move with this finger itself. And here you have another finger. So there is another joint here. Now, if you consider two strings, so you consider this blue string. So it is wound in this manner and it terminates on the other finger. And you have another string which is the red string. So you wind it in this manner and it terminates here. Now when you close this, when you close it, the blue string, it goes into relaxation. The red string goes into tension and it pulls. So it gets wound on this, and subsequently you find that this finger closes. When you are opening this, it's the red string which goes into relaxation and the blue string goes into tension. That's when it opens up and it winds on this pulley and it pulls this. So this link opens up. So you can see that just using these strings and how they're wound on this, you can obtain motion of opening and closing. Now what we have got here is what we call as the principle of opposition space. It's the implementation of the principle of opposition space, and we are familiar with this motion when we move our hands. So we developed mechanisms to demonstrate this, and you can see over here in this video that uh, you can move this. So as you move the joint over here, you can see how the strings are wound. So as you move, let's call this as the active finger, the passive finger automatically moves opposite. Okay, so you bring it closer. So this is implementing this. But here, the problem is that the axes are fixed and the axes are not permitted to move. But suppose you want the axis to move. So let's take this case. Let's take this case where we have two joints now. Focus on the second joint. So you can see the axes are able to move, but this joint is just following the other joint and exactly in the opposite direction. And that is because of the string tube mechanics. Okay. So this has been modeled using bond graph. So you can see how it follows. So this has been modeled using bond graph. And you can also implement this in the active form. That means here you are doing you're using a control strategy. So you are having one finger which is an active finger which is passing on the commands to a passive finger, and the passive finger just follows the active finger but in the opposite sense. So you can model the dynamics of the active finger joint. So here you have the torque that your active finger is applying, the change of momentum captured by this inertia, and you have the strings, the winding of the strings represented by these transformers. You can also take the joint friction into account, and that is given by uh, so we have already discussed this idea of the effort and flow. So now, as far as a passive joint is concerned, here the motion is coming from this string tube only. So you can see that the tubes are terminated on the proximal link and the strings are terminated on the distal link. So the windings, the sense of the windings is opposite for the red and the blue strings. The bond graph for it is here, but here now the active finger is passing on the motion to the passive finger. So the motion is coming from these transformers to this joint, and it is responsible for changing the momentum, angular momentum about this axis for this passive finger. And you can also model the joint friction. So if you compile, if you put them together, you assemble them, you can model this unlike configuration uh, using a bond graph model, and you can work out the tensions in the springs. You can also take into account pre-tensioning. You can model the joint frictions, a number of aspects which are related to prosthetic joint motion transfer. So this is briefly about some work on prosthesis. I'll show you another interesting work which we have done using prosthesis, that is application to a 3-joint prosthetic finger. Here we have modeled a 3-joint finger. Now here we are dealing with redundancy. So here we have an under-actuated system. So you want a particular trajectory to be followed, so you have to tune up the impedances pertaining to these joints. And the bond graph model for this, I'm not explaining in detail, but the bond graph model for this is over here. And we are making use of the string tube dynamics itself. You can have a joint-to-joint PID controller, and here is how the bond graph representation of the PID controller. So you can transfer motion from the virtual finger to an active finger. Okay, the virtual finger is something what we have as a concept in our CNS, our central nervous system. So it actually advises us the kind of motion that we should follow. And accordingly, the efforts are applied on the joints of the active finger through the tendons and the muscles, such that this active finger is able to perform its motion. Now this active finger has got to further transfer motion to the passive finger, which is the prosthetic finger. So that task, so here we have 3-joint finger mechanism with position control. So we have done position control also here, and how the position is controlled, a particular trajectory has been given. Here we have position control of an active finger tip. Here we have got active passive 3-joint finger mechanism, and here also we have shown intermediate positions. So how the position control is done, the trajectories for the active and the passive joints. So we are actually performing what we call as a operation which is just going up and down like this. It's something like when you're stitching or when you're writing. So your finger, the joint between the finger, thumb and the index finger, it goes back and forth, up and down. So using a combination of this, you are able to realize a number of useful tasks. So here, let's see the animation for this. You can see that the finger goes up and the tip goes up and down, and in the process, because we have also adjusted the impedances at the joints, you are able to get the motion of the tip, and also you are able to obtain the angular velocities at the joints corresponding to the active and the passive joints. And you can see that they exactly follow each other. So they are exactly equal and opposite motions in this particular case. The real challenge is actually while controlling the force. So we have also got the model for the force control, and this is done in bond graph like this. So here we our natural systems are blessed with certain sensors. We have uh, certain devices in our system which help us to measure the forces. And when you implement this force control model, since I have less time, I'll just skim through it quickly. Uh, we are providing a force like this, which is just going to build up, then remain stationary, and then it's going to go back to zero again. So if we do that, so it's applying. So to follow this particular trajectory, you want a particular force profile to be followed, not a trajectory profile. You can't do both together at the same time. And we have force control applied to the active passive 3-joint finger mechanism. Yeah, so here we are doing force control. So you can see the force, we come to a particular level of force, we hold it for some time, and then we release it again. So this is how it appears as the, all this is based on bond graph models. Okay. So after this, I'll just give you a brief of the modeling of synovial joints that we have done. So here we are dealing with the mechanics of carpal bones, that is wrist bones, and the ligaments. So here we have developed models using bond graph. We developed a non-linear stiffness model in order to model the cartilage. But unlike the finite element method, we are not required to discretize the soft cartilage material. So computationally, it is a little simpler, but it is at the cost of not taking into account the inertia of the cartilage, which is almost negligible in that sense. So you can see that as you squeeze the cartilage, you get a higher and higher opposition force. So it's not that you can squeeze it indefinitely. You can come up to a particular level. You can't squeeze it beyond that because the force it would become rigid. So when you model this using bond graph, and I'll just show you the animation. So here you have got this ball which is falling into a bowl and then just following the trajectory, and you can see the normal and the frictional forces, tangential forces that are encountered. Now this particular ball is just obtained from a point cloud. It is not, we are not using the equation of the circle, but we are just using the information of a point cloud. And also for this bowl, the geometry of this bowl also is in the form of a point cloud. So we apply this idea to several important biomechanical problems, and I'll show you a brief idea of the ligament and tendon wrapping that we have modeled and simulated. So we have taken the tendon mechanics, the non-linear mechanics of the tendon and the ligaments. We have used a similar model as the cartilage, but now we are dealing with the periosteum. This is the model. I'm not going into detail of this, but if we are to actually see how the wrapping phenomenon is done, you see an ellipse over here, but this ellipse is actually obtained from point cloud. It's not the equation of the ellipse. which is used. So it's a point cloud. It's just for demonstration. So here you can see that as the ellipse turns, the ligament, it wraps on this and it maintains some kind of gap that is on account of the periosteum. Here, suppose you have a combination of two ellipses like this. You don't know at what point they will come in contact with the string. So when you do this, you can see how the wrapping is done. So the wrapping is done. You can apply this to a number of three-dimensional case, for instance, and you have the string that is being wrapped around a cylinder, and you can see the different views of this, and as it wraps, how the tension increases. So once again, so this is how you can see how it has been implemented, all using bond graph. Now we come to the actual actual biomechanical problem. You have the bone, and here you have the metacarpal bone, the index metacarpal, and the end of it, and one end is tied to this. So here, when you run this, you can see how the wrapping is going to take place. It's an irregular geometry of the bone, not known, and how this, uh, as you turn it, what kind of force, what kind of tension develops on this. So this is all what you could capture because you had a model. Actually, these experiments are very difficult to perform in vivo. You won't expect um, these kind of experiments to be done in vivo, and so you have to depend upon models. So there are a number of other things which I wanted to show you. I'll show you something about soft contact dynamics. One of my scholars' work, where we have discretized the soft material as finite element and integrated it with bond graph. So I'm going to skip this theory part, and I'm going to come to this part where we are actually, you have the soft material, the layers of the soft material, and you can see there is this disk rolling on the soft material and how the layers align. So here below you have the normal as well as the tangential forces shown. So the normal forces in red and the tangential forces in blue. Similarly, we also have another example here where we're dealing with this ellipse, and you can see as this ellipse is how the force profiles, how it changes. So how dynamically you can calculate, because the area of contact is changing as this takes place. The area of contact changes, the dynamics changes, and it's all captured beautifully using bond graph. So come to the next slide. Here's another example. So I think we are approaching the the end. So I would skip this topic on musculoskeletal actuation system. That's also very interesting, but due to shortage of time, I'll just come quickly to the conclusion part of my presentation. And here we have We have done a lot of work on the applications of bond graph. We have used it in our learning and teaching at NIT Jalandhar, especially at the mechatronics laboratory. We have applied it to problems of biomechanics. What you have seen in this presentation is the application of bond graph to biomechanics, dynamics of mechanical and biological systems, especially musculoskeletal actuation systems. And we have applied it to prosthesis, a class of prosthesis. Soft contact manipulation and rolling has been modeled. It's a very challenging problem if you attempt it. Robotics and mechatronics, we work on this and we have it in our teaching, we have it in our research, where dynamics, specification for actuators and sensors, power supplies, drives and controllers, all these are determined. And we have also applied to mechanisms, some of which you have seen, especially gear train mechanisms and many other interesting developments. Finally, I would like to show you a picture of Professor Henry Painter, the originator of the bond graph approach. And he was a recipient of the Rufus Oldenburger Award, which was conferred on him. It's one of the highest awards in ASME by the Dynamic Systems and Control Division. And it was awarded to him during the annual winter meeting in New York by Donald N. Zweig, the president of ASME at that time. And he was awarded this. He was Professor Painter was a professor of mechanical engineering at MIT at that time. And he was given this honor in recognition of his creative accomplishments in all aspects of dynamic systems theory and practice. His inspiring example to students and colleagues, and his supreme enthusiasm. His accomplishments include, but are hardly limited to, innovations in fluid transmission line and fluid transient theory, seminal contributions to analog, digital, and hybrid simulation methodology, and development of an integrated notational and computational framework for energetic systems called bond graph. And Professor Henry Painter, when he originated bond graph in 1959, and later on in 1997, this is how he looked. And here in India, the idea of bond graph was propagated by Professor Amalendu Mukherjee, who was at IIT Kharagpur. He is no more now, but he was also my teacher, and he played a major role in the spread of bond graph all over India. And he was also the developer of the Symbols software. Earlier, it was a Cosmo and then Symbols. And he has got students all over the country who deal with bond graph. And here we have Professor Geneviève Dauphin-Tanguy from Lille, France, with whom I have had a very active collaboration over several years since 2000. I know her since 1997, and I've actively collaborated with her since 2000, and she collaborates with me even now, although she's retired. A very active and very enthusiastic worker. And here in the audience, we have a number of bond graphers. We have Professor Karmakar, we have Professor Arun Samantroy sitting here. So a number of stalwarts from India. This was a picture taken in 2011 possibly at IIT Kharagpur in the mechanical engineering department. This is the group that I have here in India in the mechatronics lab, and this is Professor Geneviève Dauphin-Tanguy. This is my colleague, Dr. Vishal. These are our scholars. They are also faculty members now, and we have some scholars here. So I have presented the work of some of these scholars during this presentation today. With this, I would like to conclude my session and If you have any questions, you are most welcome. Thank you very much. Hello. Hello, madam, your audio is not clear. I
Ma'am,
can't,
your audio is not clear.
madam, I can't hear your audio.
Ma'am, your audio is not clear. Um, if anyone has any query or any questions, now you can unmute yourself and please ask a question, or you can put your question in chat box also. Anyone have any questions, please? So I think, sir, there is no any question.
Yeah.
So
So
thank
actually,
you very much, sir.
it's a tough topic, and it takes time to understand. So certainly, it
Uh,
requires a lot of attention and seriousness. I can
Thank you
understand.
very much, sir. I am very confident that this session on bond graph and its application in robotics will surely benefit the participants and will open a new field for study and research in this field. Thank
Yeah,
you
yeah,
very much, sir, for joining us.
yeah. Thank you very much. Thank you very much. Thank you very much.
Thank you, sir.
Yeah.
So, with your kind permission, may I conclude this session, sir?
Certainly, certainly. Please go ahead. Please go ahead.
Thank you very much, sir. Thank you.
Yeah, yeah.